Hello, here's our Lab 11B walkthrough on the difference of means test. So let's get into this. First, we need to know, when do we apply this test? When are we looking at a difference of means as opposed to a single test of means? And it is the case that if we have two means, but they're from paired data, remember what paired data is? It's where each data point corresponds to two observations. So we could have a pre-post observation, like a test score, or we could have two different readings on the same location. In all these cases where we have paired data, we just take the difference of each score and do a test of means with one data set. So this was covered in Lab 11A, I should say here. So we're looking at the case when our data comes from two different samples, two different pools. And in theory, what this means is we have population 1 and population 2. They might come from the same population, but maybe there was a different on the two groups. So maybe these are the people who received one medication and these are the ones who received a control. So from each of these populations, we take a sample. And from each of these samples, we have a mean, X bar 1 and X bar 2. We also have the standard deviation of the first sample, the standard deviation of the second sample, and the sample size. They could be different. And if they are different, it is always a test of difference of means. Having different sample sizes is an indication that we're not dealing with paired data. So we have these statistics observed from our samples. How do we know whether the real question we're answering is, here we go, is, I got to undo this, is mu1, our population means. Population. This difference, usually 0, that's our test. Is there a difference between our two population means? Okay, so the first thing we do is we say, hey, this difference that we found, P1, not P1, we're not looking at proportions, we're looking at means, X1 minus X2. This comes from some kind of distribution. Okay, and so the standard error of this distribution follows this formula. S1 squared over N1 plus S2 squared over N2, we take the square root. So that's the standard deviation of our sampling distribution. So we're assuming what we observed comes from this. So this describes my sampling distribution. I already talked what these values are, the standard deviations and the sample sizes. And for this test, we always use the degrees of freedom, which is N1 minus 1 or N2 minus 1 for our t-test score. So let's first look at how to do our confidence intervals. So, first let's look at what our assumptions are. If we are going to use this test, we need to make sure we have independence, both within our groups and between the two groups. That means every person within the two groups are independently sampled, usually achieved by randomization. And lastly, we need to check the same rules of thumb for outliers for both groups. So if you remember from the previous lab, N1 has to be greater than 30, and N2 has to be greater than 30. If not, no clear outliers. So we have to check within two standard deviations of each other. So let's start this test. So a very good example is two versions of exam that are given to two groups of people. You know, you have an exam, got your version A and your version B. They're given to two groups of people. So each person taking the exam only takes one version. So they're not paired. So the professor has some statistics from the exam, and after sharing these statistics, the students say, it's not fair. Version B was harder than version A. You can say version B, the average was 71%. Version A, the average was 79%. And so the students are up in arms. Hey, you gave us a harder exam for version B. And so we say, wait, we can conduct a test of sample means with this. So our test is this difference between the two test scores due to chance? So our null hypothesis will be X. It's concerning our population. So mu1 minus mu2 is 0. This is saying the difference of test scores is 0. Of all people who ever would take this test, there's no difference. The alternate says, no, of all people who take this test, it's not 0. It's between the two groups is not 0. So this would be the unfair exam. One is harder. Here is they are equal. Okay, so this is a hypothesis we're testing. So let's verify our conditions. Let's check for independence. That would be achieved and were shuffled and randomly passed out. So let's assume independence. Now let's check our normality. Are our sample size bigger than 30? Looks like for the first set, yes, it's bigger than 30. We're good there. The second set's kind of small. So let's look at that. So for version B, I'll say version A and greater than equal to 30. Version B has n less than 30. So let's check. We got to say 27% plus 2 times the standard deviation. What was the standard deviation of version A? Or sorry, version B was 20. So 2 times 20 and 27 minus 2 times 20. That's what we'd expect to see 95% of our data. So we're going to say our data should be between, what was the average score? Excuse me, the average score was 71.4. So we would expect to see 95% of our data between a 34 and a 114. So if we look at our data, we do have a 32%. That's our minimum score. The minimum score is outside this interval. One data point is so there's some concern about that point being an outlier, but it's not that far outside, and in fact, what I would expect to see in some scores. So let's continue without worrying about that data point. So this is just some analysis to kind of see what we're at in terms of is our exam reasonable? Is our analysis reasonable? Okay, so since we have 2 different samples, we're going to use a different standard error for evaluating our hypothesis test for this. Our pooled standard error will look like, oh yeah, this is the same formula. So here's our pooled standard error for the 2 exams. So let's find it. We got SA. I'm going to get all this information from my chart where I can see it. SA was Then A was 30. That's all the information, all the statistics that I've gotten. And I want to know that information, calculate my standard error. Check to see that you got the same standard error as I. Means our standard deviation of our sampling distribution is 4.62. So now we can use that to find our 95% confidence interval. So our formula for this is our point estimate. This would be SA minus SB, XA minus XB, the difference of a means, plus T star times SE. Again, where does this T star comes from? We want to cover 95% of the data for our confidence interval. That means whatever distribution we have with these degrees of freedom, we need to make sure we have 0.025 in the tails. So let's find our confidence interval. I'm going to say QT 0.05 divided by 2 for the tail. And we have to use the degrees of freedom, the smaller of the two minus 1. So N is going to be the smaller of the two sample sizes, which was 27. That's our QT. That means we're going to go XB, XA minus XB plus that value times our standard error. Same thing minus. This means we're 95% likely to have this kind of distribution. So we can say with 95% confidence, the difference between the two sample that means we're 95% certain the difference lies in this range. Now, since 0 is in this range, 0 is a plausible difference. This means it's plausible to find the answers we did. I should say this, if tests are equal, it's plausible to find the differences that we did. That's our 95% confidence interval. So make sure you take care to get all these steps. Now we can repeat the same analysis using p-value. So it'll be a very similar process. We're going to calculate the p-value using our standard error. And so what we see is our score, t-score from before, was instead of x minus the null over SE, it'll be x1 or XA minus XB minus the null. And our null, for most cases, will be 0 because we want to know, is there 0 difference? So that's our t-score. And this test statistics falls on our t distribution with degrees of freedom 27 minus 1. So we observed 1.147. And so we want to find what's the probability of it being outside 1.147 and negative 1.147, the two-sided probabilities. So now we can say PT of what we found. Degrees of freedom 27 minus 1. Ooh, and I got to say 1 minus to get the upper tail. And then I'm going to double that. So we got a p-value of this, which is greater than, I think we're looking for a 0.1 significance, 0.1 significance. We sing the song, p-value getting too big, no evidence for alternative. So we say we fail to reject the null hypothesis. There is no evidence for the alternative, which states that the tests are different. So we came to the same conclusion as before. Okay, so this is pretty intense. Make sure you follow these steps. And if need be, I've recorded a video for one more example. Example on diamonds will be the next video. And birth weights, I want you to try this yourself. Although I believe all the work for this is also in the textbook, so you can check. Keep practicing. Practice makes perfect. Till these ideas are in your brain. And I'll be there for questions. Anything you're stuck on. I'll see you in class.